We already got to know some structures in the previous chapters. In this chapter, we will now go into this in detail. At first, again a list of the structures known to us. If we now take a simple body whose length is much longer than its cross-sectional area, then we call this body bar or rod. Such a body can only transfer force in its axial direction, either through tension or compression. If we have a geometrically identical body which is not loaded with a force on its axis but carries a load perpendicular to its axis, we call this body beam. If such a body is then additionally bent, we call the body arc. If we have several bars or rods or beams which are connected to each other, we call these connected bodies frames. In case of a two-dimensional body whose thickness is much smaller than the characteristic length L, and if the attacking forces are on the same plane, this body is called disk. However, if the forces are perpendicular to the body, we are talking about a plate. If it is a curved plate, the body is called shell. In this example, we now have a table with a dead weight. This table has two legs which support the table and ensure that the table does not fall to the floor. In this case, the legs are the supports of the table. The top of the table exerts a force on the legs. According to the law of actio equals reactio, the legs exert a counter-reaction on the table. This reaction can be shown in the free body diagram. We had already talked about the degrees of freedom in a previous lesson. Here again to repeat. In two-dimensional space, we know that a body can only make three different movements. First, the translation in the direction of the first axis, then the translation in the direction of the second axis, and finally, the rotation around the axis that is perpendicular to the two-dimensional plane. We can express this relationship with the equation F equals 3 minus r. In order to compensate for these degrees of freedom, we are now introducing the supports. In this example, we have a seesaw that is held in the middle by a support. The support itself is mounted on wheels on the floor. With this support, we have a support reaction R equal to 1. We know that the seesaw cannot move translationally towards the ground. However, the seesaw can move translationally to the right or left. In addition, the seesaw can also rotate. In order to represent this kind of support in a simplified way in sketches, this symbol is used to represent the simple support. If we want to catch the axial component of the translational component, we need a support that is firmly connected to the ground. In order to represent this kind of support in a simplified way in sketches, this symbol is used to represent the hinged support. Finally, if we want to prevent rotation, we have to design the bearing so that all three supports reactions occur. To represent this type of support in drawings, the body is usually connected to a wall without a joint. The wall is then shown as a hatched area. We have already learned in lesson 3 that in a two-dimensional problem we have three conditions for equilibrium to prevail. These are the three equilibrium conditions. The condition that all forces of the x component of the coordinate system are equal to 0. That all forces of the y component of the coordinate system are equal to 0, and that all moments around any point, here point 0, are also equal to 0. This applies to an xy plane. Since we have three equations here, we need three unknown support reactions, that is R equals 3. These supports can be composed of a simple support and a hinged support, or of a single fixed support. If the support reactions all add up to the number 3, that is R equals 3, then the formula of static determinacy is fulfilled with F equals 3 minus R equals 0. Unfortunately, this equation cannot be applied everywhere. In this example, we have a beam with a diagonal force F load acting on it. The beam is supported by 3 simple supports. So we have 3 support reactions. R equals 3 and the equation F equals 3 minus R equals 0 is correct. Nevertheless, the beam can move horizontally because the supports can only absorb the vertical force component, and therefore the sum of all horizontal forces is not equal to 0. Such structures are also called kinematically indeterminate. There are therefore further conditions for statical determinacy. There must be exactly 3 support reactions. These must fulfill one of the following 2 conditions. We can have 3 forces, but they must not all be parallel, and the lines of action must not intersect at one point. This is the case, for example, with a beam that is supported by a simple support and a hinged support. In the free body diagram, we see that we have 2 parallel forces in the vertical direction, but the third force is in the horizontal direction, and the forces do not all intersect at one point. So this body is statically determinant. The other variation is that through support reactions we have 2 forces and 1 moment. Again, the 2 forces must not be parallel. This is what we have, for example, with a body with a fixed support as shown here. In the free body diagram, we now see that we have 2 forces and 1 moment at the position of the fixed support. In the free body diagram, we now see that we have 2 forces and 1 moment at the position of the fixed support. Thus, this body is also statically determinant. The static determinacy depends only on the supports and not on the load. In the next example, we have a system where a beam is supported by 2 hinged supports. As we know, we need exactly 3 support reactions to fulfill the static determinacy. In this system, however, we have 4 support reactions, so this system is statically indeterminate and has 1 degree of static indeterminacy. The support reactions can thus no longer be determined for rigid bodies. In order to determine the support reactions of statically indeterminate structures, a deformation must be assumed, which is, however, the subject of the strength theory. Now we have intensively discussed the static determinacy for 2-dimensional bodies. Going back to degrees of freedom, we know that we can move 2-dimensional bodies horizontally in the direction of the x-axis, vertically in the direction of the y-axis, and rotationally around the z-axis, if we assume that the body lies on an xy plane. So we have 3 degrees of freedom that we have to balance with supports. The equation for the static determinacy is F equals 3 minus R equals 0. Now, with 3-dimensional bodies, the whole thing looks a little different. Here we can move the body translationally, horizontally, vertically, and now also in depth. As far as rotations are concerned, we can rotate the body around all 3 axes. We therefore have 6 degrees of freedom, which must be compensated by supports. The equation for static determinacy is therefore F equals to 6 minus R equal to 0. The supports differ between 2-dimensional and 3-dimensional bodies in the following points. First of all, the simple support. This has a support reaction of 1 in both 2-dimensional and 3-dimensional bodies. It is only used to catch translationally in the axis in which the simple structure is attached. The other 2 axes and all 3 rotations are still possible with the simple structure. With the hinged support, we have a support reaction of 2 for 2-dimensional bodies since all translational movements are absorbed by the support. With 3-dimensional bodies, too, all translational movements are absorbed, so we can set the support reaction to 3. As with 2-dimensional structures, The fixed support also absorbs all translational and all rotational movements in three-dimensional structures, so that the support reaction of the fixed support in three-dimensional bodies are equal to 6. Of course, there are exceptions with three-dimensional bodies where the support reactions can be 4 or 5. For example, with a shaft that is stuck in a tube that allows a translational movement and a rotational movement. Now, in statics, we usually have not just one body, but several. Here in the example, we have 3 beams which are supported at the ends by fixed supports. The left and the middle beam are connected by a strut. The middle and right beams are connected by a joint. Now we set up the free body diagram. We know that with fixed supports we have 3 support reactions, 2 translational and 1 rotational. So we can give R equal to 3 for each of the supports. The strut can only transmit a force along its axis. So here we have joint reactions which we designate with the letter V. Since the strut can only transmit a force in one direction and the bodies can still translate or rotate relative to each other, the joint reaction V is equal to 1. In the joint, the bodies can no longer move in translation relative to each other, but they can rotate. Here, the joint reaction V is equal to 2. If we now use the letter N for the number of bodies, we can use the following equation for static determinacy in multipart structures. R plus V equals 3N. If we apply this equation to our multipart structure, then with the 2 supports, we have a total of 6 support reactions, and with the 2 joints, we have 3 joint reactions. So we can write R plus V equals 6 plus 3 equals 9. Since we have 3 bodies, the degrees of freedom of the bodies here is 3 times n, so 3 times 3, therefore also 9. Thus, we know that this multipart structure is statically determinant. On this slide, I want to introduce the 3-hinged arc. First, we have an arc which is supported by a hinged support and a simple support. We have one body, so 3 degrees of freedom. The hinged support has 2 support reactions and the simple support has 1 support reaction, so the body is statically determinant. Now, in the case of the rigid body, the body is thus optimally supported, but in reality that is not the case, because there are strength problems in the body, because the simple support can move further. So it is better to use a hinged support instead of the simple support. However, this leads to the fact that we now have 4 support reactions and are thus statically indeterminate. To compensate for this, we can insert a hinge in the body. This means that we now have 2 bodies, so the degrees of freedom are now 6. However, due to the hinge, we have 2 joint reactions. Together with the 4 support reactions, all 6 degrees of freedom are served and the system is statically determinate. This type of system is very common and is called a 3-hinged arc. The following is a body which is very elongated. Since this body has a great length, it must be supported by several supports. To avoid strength problems, we have a hinged support at the one end and the remaining supports are simple supports. Even though we are working with rigid bodies in statics, we should keep reality in mind. The system now has 5 support reactions with the 4 supports, so we have a statically indeterminate system again. To counteract this, the body can again be divided by hinges. If we divide the body at the various points by 2 hinges, we then have 3 bodies, that is 9 degrees of freedom, 5 support reactions and 4 joint reactions due to the hinges. The 2 hinges and the supports thus equalize the degrees of freedom of the system, and we have a statically determinate system. Such systems are also called hinged beams. A brief review of static indeterminacy. We know that our degrees of freedom F can be calculated by F equals 3n minus R plus V. Here n stands for the number of bodies, R for the support reactions, and V for the joint reaction. If F equals 0, we have a statically determinate system. If F is greater than 0, then the system is movable. If F is less than 0, we have more support or joint reactions than we actually need for the degrees of freedom, and thus a statically indeterminate system. For the static indeterminacy, there is the degree of static indeterminacy, here denoted by the variable x. It indicates the degree to which a system is statically indeterminate. Now, if we have a static determinant system, there is a possibility to determine the kinematical determinism. To do this, the equilibrium conditions must be written down and the equations converted into a linear system of equations. This contains the matrix A multiplied by the vector x equal to the vector b. The matrix A contains coefficients that arise when the equilibrium conditions are set up. The vector x contains the unknown support and joint reactions, and the vector b contains the forces acting on the system. Once the linear system of equations has been set up, the determinant of the matrix A can be set up. If the determinant of A is then non-zero, we know that the system is both statically and kinematically determinate.